welcome. It's a very particular pleasure to welcome our speaker, Simon Lavington. He is known to many of you. He is perhaps the preeminent historian of early British computing. He's published widely books, articles. He is a long-standing member of the Computer Society, Conservation Society, and a long-serving member on its committee. He is also the creator of a really comprehensive, almost defining database of early British computers called Our Computer Heritage. And his distinctions are quite endless. It's a particular pleasure because of the topic on which he's talking, which is Max Newman and early British computing here. Why it is a particular interest is because there is a kind of black hole in the history of computing, and that is to say, we know that there was huge knowledge and expertise accelerated by wartime work in development and innovation in computing. But because of the secrecy under which that knowledge and expertise was blanketed, it's very, very difficult to trace the way in which this knowledge was disseminated into civilian life. The content, the material, the sources were actually secret for many years after the war. So it has been some while actually to get to the point where we can actually trace, if you like, a diffusion narrative from wartime work into modern times. And Max Newman is, of course, a key figure in that. And Simon's excavation of that particular influence is particularly welcome and, you know, an early and hugely welcome antidote, if you like, to this black hole of post-war influence in the diffusion narrative of wartime expertise. Simon, over to you. You're muted, Simon, you're muted.
Yeah, that seems to be it.
Yep.
Okay. Good morning. Good afternoon, everybody. Yes, I'm going to speak about Professor Max Newman, Professor of Mathematics at Manchester University, and his plans to use a Colossus type machine at Manchester for investigating problems in pure mathematics. We have a fair amount to get through in this talk, and I realize now that, oh yeah, here we are, change the next slide. So we've got about 6 sections to get through. And first of all, I think it's important to understand exactly what Newman's vision was in 1945 or 1946. And then we'll go on to describe his grant detail, his application to the Royal Society for funding in as much detail as we have discovered, and then some practical problems in his research in implementing his aims. That will lead on to a sort of a new entry in the Manchester scene at that time, some hardware people, engineering people, and that led to an artifact which was used for mathematical problems by Newman and his colleague. And then we tackled the aftermath from 1951 onwards. So Max Newman, what was his thinking, do we believe, in 1945 and 1946? Well, of course, Max led the outstandingly successful Colossus code cracking team at Bletchley Park during the war. So it is natural to imagine that his thinking immediately after the war was influenced by his experiences. So we should ask ourselves what was happening at the successor of Bletchley Park, namely gchq, in the immediate post-war years. Well, mostly they were using special purpose machines, continuing to use what were termed rapid analytical machines. For example, two of the Colossus 2 computers, let's call them computers, were retained after the war and were working right through the 1950s. 4 new Robinsons were obtained, and then there was a succession of new rapid analytical machines built in the next few years. Why did GCHQ major on these special purpose machines? Well, it's really for cost-effective purposes, for reasons. Oedipus, for example, that was a machine designed to search rapidly through a dictionary of code words seeking matches. And it was able to do that operation at about 10,000 times faster than conventional general purpose computers of the mid-1950s. GCHQ, of course, also used general purpose stored program computers, but not for some while. In this respect, the Brits were about 3 years behind the Americans. And one of the first general purpose computer they installed was a machine that we'll refer to towards the end of my talk. So this sort of environment must have been in Max Newman's mind when he thought about challenging some of the problems in pure mathematics. There are many unsolved problems that would have appealed to him. The interesting thing is that these problems can be tackled, a lot of them, either by logical reason or by numerical evaluation. So let me give you a simple example, which is not actually one of the problems. Mersenne primes. These primes are defined as numbers of the form 2 to the p minus 1. And the question is, are there infinitely many such Mersenne primes? To answer this, one can set about evaluating successive primes. The difficulty here, from the computing point of view, is that the numbers are very large, multi-digit numbers, and the compute time to check for primality, check the factors, is rather long. So let's go on to Newman's January 1946 grant application to the Royal Society. I'll introduce some photographs of the players first, and then give some extracts from Newman's grant text, and let us try and deduce what he was on about. And to do this, it's appropriate to describe some opposition to his grant application, and then some comments from reviewers and funders. In the end, of course, he was successful and the grant was funded. So what are the players? Well, there were 3 particular professors at Manchester during the relevant years, and the dates that they held their chairs is given under their names. They were all friends. They were all the same age, age 49 in 1946. Patrick Blackett has been best man at the weddings of both Douglas Hartree and Max Newman's wedding. They had different skills. Patrick Blackett was an experimental physicist. Douglas Hartree was a mathematical physicist, and Max Newman was, as we know, a pure mathematician. Of the 3, I think Blackett was the most influential. He had held various government appointments during the war, and he had the ear of those in authority. Douglas Hartree's contribution to our story is principally, I think, because he was the go-between, the means of communication between the immediate post-war American computing projects and the embryo projects in the UK. So let's go on to consider Max Newman's grant application, and I have 5 extracts. Now, I'm sure you can't read what's on the screen, so I've helpfully summarized the points made on each of these extracts. And the first point is that there were some interesting mathematical problems to be solved, and Max Newman's ambition was to address those. Secondly, why should such research take place at Manchester? Now here, Max Newman had to be a bit careful in what he said. He, of course, could not mention exactly what was happening during the war at Bletchley Park, but he hinted that himself and a couple of other colleagues had relevant experience during the war. He also pointed out that the professor of electrotechnics at Manchester at that time, Willis Jackson, had expressed an interest in the computing project. And finally, Newman had arranged that some surplus government electronic equipment had been loaned to the university. Collaborators, Newman went on to say that he felt that the National Physical Laboratory would be there to advise, but particularly he focused on the Dollis Hill Research Station of the Post Office, because it was the engineers from Dollis Hill who had designed Colossus, and Newman was confident that they would help, and furthermore, that the Post Office would manufacture the apparatus. Pointed out one of the problems, perhaps the major problem of the whole research, was recruiting a chief engineer who had a foot in both the electronic camp and the mathematical camp. You might say a rare beast, and so it turned out to be. And finally, Newman summarizes his application as being to investigate electronic machines, and notice the plural here, machines to deal with mathematical problems. Now then, on to the scene marched Sir Charles Gorton Newman, Charles Gorton Darwin, who was the director at that time of the National Physical Laboratory. Let me pause for a moment to see whether I can get my voice back. Now, Darwin was an eminent scientist, and he objected in strongest terms to Newman's research proposal, principally on 2 grounds. First of all, he said that NPL itself was in the process of designing a computer, and the emphasis is that he felt that his was going to be the British national computer, and there was no need to fund any other project. But secondly, he objected to the way Newman proposed to tap into the Dollis Hill resources, because NPL itself wanted to tap into those same resources. The Royal Society, in view of this opposition, obtained the services of some grant reviewers, of which I have quotes from 2 of them, Hartree and Patrick Blackett. Hartree pointed out that this was interesting research to do, and also that the use of electronic machines in this field of pure mathematics would be very much experimental. Blackett was more forthright. He pointed out that there was a difference between NPO's general purpose computer and Newman's special purpose machine. And it's clear that both Hartree and Blackett envisioned Newman's machine or machines as being reprogrammed by resoldering. The conclusion, nevertheless, was that the grant was financed, and Newman got his money in June 1946. £35,000 doesn't seem a lot these days. It's equivalent to about £1 million, and had to have special Treasury permission. 20,000 of the grant was to go on equipment, the rest on salaries. It's interesting to show also some subsequent supportive quotes about Newman's research, and to make the point that the view of Newman's machine is as rather different and special from others being designed at the same time, persevered until at least the middle of 1949. And a view of the events that I'm going to describe later in the talk, this is rather significant. So in summary, Newman's project was special in that it was the only one intended to be used for the investigation of problems in pure maths, and was not intended to do computing jobs of, as Newman said, immediate practical utility. So on with Newman's grant application, grant project, and how he spent his money. This is a chance for us to introduce some other players as the emphasis changes. We introduced the Ministry Supply, which is which was the forerunner of the Ministry of Defence. We introduced the Telecommunications Research Establishment, which was the heart of government-sponsored radar research during the war. And we introduced the Manchester firm of electrical engineers, Ferranti Limited. So the first problem that Newman addressed in terms of his project was his search for engineers. And Dollis Hill, the post office, quickly made it apparent that they could not help, despite what the former impression had been. They said that they were overwhelmed with the job of redesigning and re-equipping telephone exchanges and getting the war-torn telephone services back up to spec. Secondly, they've been asked by the Ministry of Supply to design a secret general purpose computer called Mosaic, which was intended to help analyze signals in guided weapons trials. The next blow to Newman was that Willis Jackson, the professor of electrical engineering, up sticks and went. He went to Imperial and he took a van load of equipment with him. This, though, created an opportunity. A new professor had to be appointed. Well, the candidate list opened with two people. It was Blackett who suggested a third person, F.C. Williams, Freddie Williams of TRE. And it's interesting just to remind ourselves of the pluses and minuses of Williams. On the plus side, he was a recognized circuit designer. He had many papers to his name, but principally he held a patent for digital storage. Now, memory devices were one of the prime problems that held up the implementation of stored program computers in the late 1940s. Williams's disadvantages was that his status was fairly lowly. The last pre-war appointment he had at universities was at assistant lecturer level. He has narrow electrical engineering interests. So was he the right person to lead a general engineering department? More crucially, he disliked mathematics and he had no computing knowledge. But nevertheless, we need to take more than a cursory look at Williams and TRE, and the next 3 or so slides are a slight digression from Newman to fill in a bit of essential background. So TRE was where Williams and his colleague, Tom Kilburn, started their storage research. And 1947 was a critical year in the relationships between TRE and the University of Manchester, to which Williams was appointed as professor. And TRE was anxious that his research should continue, and therefore they seconded his colleague Kilburn to help, and later on another colleague, Jeff Tutul, and they provided resources for Williams to continue his research. Meanwhile, other staff at TRE had got interested in computing, and the group was led by Albert Utley on the hardware side and Philip Woodward on the mathematical side. And early in April 1947, they read the reports coming out of John von Neumann's laboratory at Princeton, the Institute of Advanced Study. And for the rest of this afternoon's talk, I'll refer to the shorthand of IAS as the John von Neumann type of single accumulator computer architecture that was an inspiration for several early projects at that time. TRE started its own computer project in the summer of '47, intent on using the Williams and Kilburn storage system, which was random access, and the RAM indeed was working at the end of '47. At Manchester, this produced the baby computer and its follower-on, the Manchester Mark I, and later the Ministry of Supply gave a rather large contract to Ferranti Limited to produce a full-strength commercial version. And it wasn't until some time later that TRIAC, the TRE machine, first ran its program. What of this memory device? Well, it was first of all known as the Williams tube. Later on, historians dubbed it the Williams-Kilburn tube. Digits were stored as electrostatic charge patterns on the phosphor inner coating of a cathode ray tube. The electron gun bombarded elements of the screen, which became charged, and by varying the type of charge distribution, you could represent zeros or ones. When these charges were interrogated by the electron beam, a voltage was induced in a pickup plate, which was on the external surface of the screen, and the signal amplified. The thing about this device, apart from being random access, which was quite important in those days, is that it used off-the-shelf components. So here are the two people responsible for those developments. On the left, Tom Kilburn. On the right, FC, Freddie Williams. their ages respectively being 25 and 35 at the time of asking. And they're at the controls of a very small demonstration computer that first worked on the 21st of June, 1948. I shan't mention more about Baby, although if you care to come to an event in Manchester in mid-June of this year, you'll find out more, and indeed see a demonstration of a reproduction. So what is the effect of these hardware artifacts on Newman and his thoughts and his project? This is the point in our story at the end of 1948 when Alan Turing is recruited to join Newman's team at Manchester, and we'll of course mention Turing more in this talk. So the latter half of 1946, Newman struggled with the question, what kind of overall architecture should he have for his mathematical machine? And to help him in this endeavor, he sent one of his junior lecturers over to the Moore School lectures in America. He and another colleague, Jack Good, visited Turing's group at NPL, and finally, Newman himself spent 3 months on sabbatical at the end of 1946 at John von Neumann's group at Princeton. So for question A, by 1947, he had chosen an IAS type of architecture for his computing machine. And as he said, the design of the machine by then was naturally placed in Williams's hands. By early 1949, the Baby machine had been expanded, enlarged in various respects, like its word length, its repertoire of instructions, and it had become called the Manchester Mark I. And this was equipped with both general computing facilities created, we can see, by the engineers, and some special facilities which bore the influence of Newman and Turing. And it's worth just a one-slide digression to say a little bit more about these two types of features that distinguished the Manchester Mark I from other computers in 1949. Well, the Manchester machine had index registers. It had a synchronized magnetic drum backing store, which allowed several drums to be placed on the single CPU if necessary, and it had a programmer accessible page address register. But I won't talk more on those. Let's go on to a couple of special areas where the hand of Newman and Turing is to be seen. Firstly, well, most computers at that time had a logical AND instruction. In addition, the Manchester machine had an exclusive OR a non-equivalence instruction. This is the modulo 2 addition fondly used by cryptanalysts. But more importantly, I think the Mark I had more multi-length accumulator facilities. And I've compared in this table at the bottom of the screen the Manchester machine with two other contemporaries. First of all, the Cambridge EDSAC, which first worked in May 1949, and secondly, with the Standards Western automatic computer, SWAC, one of the very early American computers, which burst into life in August of 1950. And I draw your attention to the central column of the table, which gives the total number of instructions in the instruction set for each machine. and then a number of such instructions which were primarily concerned with manipulating the accumulator. And one would expect to be able to load, store, add and subtract into the accumulator, and maybe another order clear accumulator. Anyway, there are a small number of such instructions, compared with which the Manchester computer had 11 computers for manipulating the double length 80-bit accumulator, the top half and bottom half of that accumulator. So armed with this working hardware at Manchester, Newman set about tackling two specimen mathematical problems. First of all, Mersenne primes. Previous to computers being applied to this problem, the highest P discovered manually was 257. And Newman and Turing set about writing programs in April of 1949 and increased the value of known Mersenne primes by a P of 353, a useful advance. They reduced the runtime of their program to 1 hour by using the Lucas test for primality and by playing a few tricks of binary arithmetic, based primarily on the observation that a Mersenne prime in binary is all ones. And the paper describing the program was written up by Newman and presented at the June 1949 Cambridge conference. It's worth pointing out that Mersenne searches soon got going elsewhere, particularly in Cambridge in 1959 and SWAC in America in 1952. The largest P that I've discovered through searching the internet in 2018, a P of 82 million was discovered. So it's, Mersenne primes is a topic that continues to fascinate computer-minded mathematicians. The second problem tackled by Newman and Turing, particularly by Turing actually, was the Riemann Zeta function, defined to be the sum from n equals 1 to infinity of n to the minus s, where s is complex. And the Riemann hypothesis is about complex zeros of that function and the fact that they, as hypothesized, lay upon a critical line. Quickly illustrate that. Here is a small section zeta function, the real part in red, imaginary part in blue, and you won't really be able to see it, but the complex zeros on the diagram are 3 in number in this range, and there are symmetrically another 3 on the right-hand side of the axis. So the job of Turing's program was to investigate some values of t and find the complex zeros. The program took about 9 hours plus an additional 8 hours of error checks, and it involved computing terms that such as the one on the screen, which has a square root function, trig function, log function, all introducing approximations. So the main worry, or part of the worry, was to get a handle on these approximations. The Riemann Zeta function was something that had interested Turing from 1939, when he started to build an analog machine rather similar to a tidal flow predictor to investigate the function. the challenge of the Riemann-Zeta hypothesis was quickly taken up by other workers. Turing, when he wrote up his program in 1953, was rather dismissive, saying that he had advanced known values of t by only by a small amount, and he said he'd made little contribution to the art. The largest figure that I've come across is some work in 2020, where the figure of t has gone up to more than 10 to the 12th. And that involved the equivalent of 7.5 million processor hours on the University of Bristol's Blue Crystal multi-computer. As a result of this, were two additional special instructions that Newman and Turing put into the specification that went to Ferranti Limited in the production of the commercially available computer. The first was a population count, or sideways add, which gave the sum of the bits in a word set to 1, and the second is a hardware random number generator. I won't say more about those special instructions at the moment, and indeed there's no surviving source documents that discusses exactly why these two orders were in the mind of Newman and Turing in 1949. Let's move swiftly on to consider what followed in 1951 when the Ferranti Mark I, the industrially produced manifestation of the Manchester research machines, came along. Let's discuss the users of that machine and how the whole computing scene developed at Manchester, and in the wider perspective, what became of Newman's original vision. Well, here is the Manchester, the Ferranti Mark I. By the way, I seem to have some red scribbles appearing on my screen. I don't know whether anybody else can see them. Certainly, they're not due to me. So let's press on regardless. So this is a picture of the Ferranti Mark I, which was installed at Manchester University on the 12th of February, 1951, and thereby becoming, as far as we know, the first commercially available computer to be delivered anywhere. This computer sat in a building, a new building, and one of the problems in setting up this laboratory was finding the finance to build a special two-story house for this computer. And this is where Max Newman's £20,000 of equipment money came into its own. The money had been unspent by Newman, and the University Grants Committee and the Treasury thought that the best thing to do with the money was to put it into a new building to house the machine, and so it happened. In the photograph, the person on the right-hand side, leaning against the console, is Alan Turing, and the people sitting at the console, two Ferranti engineers, Keith Lonsdale and Brian Pollard. Brian Pollard was the manager of Ferranti's computer department at Moston in Manchester, which was about 3 miles to the north of the university. So what was this computer used for at Manchester? was it indeed used for the sort of mathematical problems that Newman had in mind? Well, here's the list of applications that were initially put onto the Ferranti Mark I at Manchester, and this list is taken from the inaugural lecture by F.C. Williams. The first, morphogenesis, or the growth and form of living things. This was Alan Turing's baby. He became fascinated by embryology, the mathematical basis of embryology, and indeed devoted the rest of his computing time until his tragic death in June in 1954 to writing programs on morphogenesis. Most of the other applications listed here are self-explanatory, perhaps not number F, the tabulation of Laguerre functions. This was Ferranti's concern in connection with a government-sponsored work on guided weapons. Ferranti didn't have a computer themselves, and so they used time on the Manchester University installation. The final entry, hydrodynamics research, is a kind of euphemism for use made of the Manchester machine by scientists at the Atomic Weapons Research Establishment who used the Manchester Mark I, the Manchester Ferranti Mark I, before installing their own computer at Aldermaston. The community of users of the Manchester machine grew so that by 1959 it had spread quite widely, as you can see on the screen. Of government establishments to use the machine, perhaps the most obvious and interesting was the Met Office. Now the Met Office needs a large computer, and Manchester was the one, Ferranti was the one they chose. Ferranti, meanwhile, had decided that it could really sell a few more of these computers, and it sold 9 in all of the Ferranti Mark I and a slightly modified version called the Ferranti Mark I Star, which had a reduced instruction set, not reduced in any significant functional manner, but reduced so that only 5 bits instead of 6 bits was used for the opcode. And of course, 5 bits corresponds to a character on the teleprinter code. You can see at a glance that most of the applications or the sites of the Ferranti machines were in some way or other to do with government-sponsored work, and particularly some implied work in defense of the country, like the armaments research establishment at Fort Hasted and the atomic weapons establishment at Aldermaston. The only one in the list which was paid for and delivered without any implied overt or covert government aid was that to the Shell Labs in Amsterdam. And interestingly, this is believed to have been the only computer, sorry, the first computer in the world to be installed without government aid of one sort or another. So where does this leave Max Newman? He kind of slips out of the picture. In the audio interviews that he did in his late 70s and 80s, he says quite frankly that he lost interest in computing. But we shouldn't dismiss him, certainly not. And at the risk of being slightly decisive, divisive, I leave you with this picture of the kind of reputation that Newman might have enjoyed on the worldwide scene. And by reputation, I mean his thinking, his relative knowledge, his vision, and his practical success. So Newman obviously started on a high. He had led the outstandingly successful Colossus group at Bletchley Park. He had ideas for how to apply this sort of technology. Furthermore, he got a grant of money to put his ideas in practice. But things didn't quite work out as he had at first envisaged. And so one has to admit that his impact on the world stage, the world computing stage, fell away. In contrast, the engineers, people like Tom Coleman, started from zero, really, in the computing field, and gradually picked up as hardware started to work and to be used. And I guess, in my mind, I have a notional crossing point of their impact on the world stage in about the latter half of 1947. Anyway, that's for contemplation. So perhaps I'll leave you finally with just a reference to pursue. There is a paper coming out in the next edition, next volume of the Annals, which describes a bit of the background to the research that has led to this presentation, and rather more about the source documents is given. And finally, if you're interested in asking questions, we realize that these Zoom sessions aren't particularly conducive to question and answer sessions. So here's my email address, and do please email me if you have any questions. Well, Doran, that's about it. So over to you.
Simon, thank you for that. And I'll now invite questions. I give my assistant in the room a microphone. Perhaps if anybody, I don't see any questions in the chat room at the moment, but if anybody would like to ask a question, perhaps if they unmute themselves and we can go, or if there's a question in the room in London. Anybody? No. Anybody online want to ask a question?
I have a question, please.
Yes, away you go.
Thank you, Simon. Excellent talk. Very enlightening. Thank you, really. I want to ask you about Darwin. Why do you think he was against them, against Newman? Because also he was against the work that Alan Turing did on intelligent machinery. He said this is a schoolboy essay. So is it his character? Is it the character of Darwin, or is it related to something else? What is your point of view about that?
I think it's related to Darwin's character. And I say this because he sort of looms in the background behind one or two other computer initiatives in those early years. And it is clear from correspondence at the time of setting up what was known as the Brunt Committee of the Department of Scientific and Industrial Research, that some held the view that if it was up to Darwin, no novel research at all would be conducted in computing outside of NPL. I mean, I never met Charles Darwin. You'll be surprised to learn, and so I can't comment personally. But I think from the correspondence, it was Darwin's authoritarian and dominant personality that drove him.
Very good, very clear. Thank you.
Can I just guys add something there? I might know somebody who can tell me a bit more. I'll try and find out because I know his daughter-in-law. So I'll when I next see her, I'll ask her and see if she knows anything about her father-in-law in that regard. I wouldn't be surprised. She's a very intelligent lady. So yes.
Well, there's no doubt that Darwin was an eminent scientist, but it just that at the time of writing, he was, I think, really obsessed with the idea of the NPL machine as the British national computer.
There's a question whether about whether the work by Newman had any connection to Leo. I'm not immediately clear what the link may be, but Simon, do you have a comment in answer to that?
I would say no connection whatsoever. I mean, Leo, well, the Lions was a go-ahead company. As you know, they sent a couple of people, Thomson was one of them, to the States very early on to find out about modern electronic aids to administration in the business context. And that led to contact with Cambridge University. And Leo was based on the Cambridge EDSAC, with additions to make it more amenable to bulk data processing.
There's a comment here from Doran Sway. Doran, do you want to say a word about Copeland and Anderson's work?
Yes. Well, one is thanks hugely for an extraordinary excavation of that episode. I was wondering, in the light of what has been about the existing canon, Anderson and Copeland have given it some attention to Newman. And it seems that this, the new research with the new sources from the Royal Society, have the opportunity of resolving or at least amending some of their positions. I'm not that familiar with what their positions are and whether and if there are, what the issues of contention might be. I was wondering whether your work helps us actually resolve or amend the positions as currently perceived by the earlier work.
Well, thank you, Doran. Yeah, I think it does help the debate. The advantage I had was in making friends with an archivist at the Royal Society who dug up a collection of relevant correspondence that had been kind of hidden away. I don't know why it had been hidden away, but it's just possible that Newman sailed a bit close to the wind in his hinting in his application that exciting things had gone on at Bletchley Park, and people didn't want outsiders crawling over this correspondence. I don't know, but in more direct answer to your question, I will refer you to the paper that's coming out in a few weeks' time, when I directly address the issues that Jack Copeland and David Anderson and others raise. And well, I hope that I try to balance the two sides, the two political sides. As many people will be aware, the whole of the modern historical debate about Manchester, its place in the computing firmament, has been sort of influenced by, on the one hand, the mathematician's view of things, and on the other hand, the engineer's view of things. and somehow a balance has to be struck. And I just hope that in a small way, I've tried to bridge the gap.
I see Bob Harvey has his hand up. Bob, do you want to ask a question?
Yes, indeed. Simon, do you know anything more about what the number 9 star, the last machine, was used for at Armstrong, Siddeley at Anstey at all?
Yeah, well, it's the design of aero engines, turbine, things like that. And of course, the Armstrong Siddeley portion, the factory division doing that work, became the Rolls-Royce Bristol outfit in the mid 1960s, and their computing activity was transferred to Bristol, Fulton, etc. So aero engines is the main thing.
Thank you very much indeed, Simon.
There's a question from someone who's logged in just as George. I wondered if George is there, whether he would like just to say a word about the question relating to information transfer, knowledge transfer between Manchester and Imperial. Do you want to add to your comment?
Someone else had, thank you for the lecture, Simon, excellent as usual. Someone else had posted a note that said how much stuff had come from Bletchley to Manchester. And I'm sure I read somewhere it was 7 ton. But I'd never heard that stuff had gone from Manchester to Imperial after that, and wondered how much had gone to Imperial.
That's a good question. You're right that Newman acquired lorry loads of ex-Bletchley Park equipment to be delivered to Manchester University, suitably stripped of its labels, etc. The interesting thing from my point of view was to examine the nature of this equipment insofar as it can be determined, and it immediately became obvious that the sort of valves, the AF valves, thermionic tubes used in the Colossus machines were not of the RF higher frequency type that Williams and Kilburn were used to. So whatever equipment, hardware had been delivered from Bletchley Park to Manchester, it's not clear whether Williams and Kilburn would have chosen to use any of it if they had not been equipped anyway by stuff arriving from TRE. So that's one side of the problem. On the matter of what equipment Willis Jackson took to Imperial, I personally don't think he took anything that would have been of significance to William and Kilburn, partly because if you look at Willis Jackson's research expertise, his interests were in dielectrics, capacitor dielectrics, which was not entirely close to the sort of high frequency electronics, pulse electronics, that you needed to know about in digital computers of that age. We do know in a book written by a Manchester engineer, A History of the Electrical Engineering Department, that the chief technician in the electrotechnics department at Manchester expressed himself, quotes, disgusted at the way Willis Jackson stuffed a lot of equipment into a van when he departed to Imperial, leaving the Manchester department looking very naked. So I don't know. I wouldn't myself think that anything that went into Jackson's van was of huge significance, either in its loss to Manchester or in its gain to Imperial.
Simon, Alan Hartley Smith has a question about whether Newman had any thoughts on real-time use of a computer.
Real-time use. Now that's interesting. It's interesting because to some extent, as far as I understand the Colossus setup, there was some interaction between the cryptanalysts and the progression of searching, checking, or whatever of the electrical apparatus. That perhaps some trial scores were produced on a electric typewriter that allowed the code crackers to adjust various parameters, various switches, plugs and switches, and refine the searches, the tests going on. That's for others to comment on, those people who know about these things. But if you mean by interaction, the interaction between a human operator and an electronic device, then I suppose in that sense, Newman had some feeling of that type of experimenting. And indeed, in his grant application and the comments on it by Hartree and Blackett, you get the sense that Newman envisaged a laboratory of, how could I say, hairy equipment that was being fiddled with, being adapted by those who were seeking to make its output, its test results, more relevant to the mathematical problems that were being investigated. So in that limited sense, I think man-machine interaction, human-machine interaction might have been in Newman's mind. In the sense of online control of gunnery, etc., I think those practical applications of online control by a digital computer of electromechanical equipment were far outside Newman's scope.
Thank you for that. I think that brings us to the end of the questions. Can I report happily that we had 107 remote participants, and a further 20 in the room here, which is amongst the biggest audiences we've had. It's a delight to see so many people in the room here, and I would like to encourage more to come along. And in particular, the May meeting we've got relates to Dollis Hill, and Rachel Boone, who may be known to many of you for working at the Science Museum in London, is talking about her PhD thesis, and the title of the lecture is From Public Service Provider to Clandestine War Workshop, the Post Office Engineering Research Station in the mid-20th century. Dollis Hill recurs in many different places in the story of the beginnings of British computing. And so we look forward to welcoming Rachel on the 19th of May, and I hope to welcome many of you as well to that meeting. And I'd like now to hand over to Doran, our chairman, to give a vote of thanks to Simon for what I'm sure everybody in the room here, and I'm sure everybody online, has found a fascinating afternoon. Over to you, Doran.
Thank you, Roger, and thank you again, Simon. Several things struck me while you were speaking. One is, what kind of history is this? And I think it had what is the signature of the kind of history you do, which is that the hallmark attention to technical detail and knowledge of technical detail wrapped in an envelope in the context of what was going on. And that's quite rare. One often finds huge depth of technical detail with very little context, or context with very little technical detail. I think in your writing, and very evident in this lecture, there was this wonderful fusion of these two very strands which are very difficult to reconcile. And I think that is what is both, which is a hallmark. It's a signature of a particular kind of history, which I think you are absolute master of. And I think that the attendance, the numbers, was both in expectation of a quality of that kind and fully vindicated by the actual delivery of the presentation. Two comments about the big picture of where this fits. I commented early on about the lack in the literature of a detailed mapping between what was going on in the war under secrecy and how it mapped out into civilian and academic computing. And I think this is one of the most detailed studies of actually that mapping. When you start considering what might have influenced, what aspects of Colossus might have influenced the architecture of the subsequent commercial machines, I think that is hugely valuable and quite rare in the diffusion narrative, in people trying to map and give account of how this expertise disseminated into industry. The other thing that struck me, which is slightly with a smile, and that is that the last person I'm aware of who specifically looked at the potential of computers in a mathematical context was, dare I say, Charles Babbage. Because for him, computers were less significant in respect of what we might call computational thing, numerical computation. He was interested specifically in the potential of machines for mathematics. For him, automatic computing was a new technology for mathematics. Now, as it happened, that it was the numerical computational side which in a sense hijacked the agenda, because that is the way you could justify it in utilitarian ways. Given he didn't build any of his engines, both agendas failed. He didn't produce machines that did major computation, and the mathematical enterprise failed entirely. And as far as I'm aware, Newman is the only other person I know who explicitly said, emphasized that the potential of computers, that wanted to explore the potential of computers for mathematical purposes. And interestingly and ironically, it was also hijacked by the numerical analysis side, by the numerical computational side, by the Ferranti procedure. So in a sense, both two mathematicians, 150, 200 years apart, had the same ambitions about using computers for mathematical purposes, theoretical mathematics, and both agendas ran into the ground. One was never fully realized, despite the aspirations. And in Newman's case, that agenda died in favor of, fizzled out in favor of the commercial machines of Ferranti and so on. So I was very struck by the repetition of the thesis of machines for computers for mathematics and the fates of these two mathematicians as something rather ironic in the evolution of the. So those were just two items of huge appreciation of aspects that seem to resonate with prior work, the canon of history, in which I think this work, which with the new resources from Royal Society, the new sources from Royal Society, has a great deal to add to an existing debate in which we still struggle to see what was really going on in the post-war years before it was in a sense swept away by the von Neumann architecture paradigm. So Simon, a rather lengthy but hugely appreciative thank you for a superb presentation. Thank you very much.
Thank you very much.